Good evening, everybody. We have an integer equation that we're trying to solve right here. Now let's go ahead and get started by finding some trivial solutions here. Let's write these in ordered pair form. The ordered pair n comma n. Again, this is by inspection. These are going to be trivial solutions. And we'll know the solution set is non-empty once we write this down. And you guys could probably notice right now that that's plus or minus 1 for m. And then 0 for n. Okay, so those are two solutions, and it's very easy to see. If you put 0 right here, it's very clear that plus or minus 1 would be equal to m. Okay, so there's two solutions. Many would call these trivial. Also, something to note, since we're trying to find all m and n. Now, m and n integers means positive or negative natural numbers, also including 0. We can observe here that n is greater than or equal to 0, right? And that's clear because the left-hand side has to be greater than or equal to 0, right? So we have a restriction on n. N is always non-negative, okay? Now what we do to get started on this is we just take the square roots of both sides and we get a plus and minus solution. That's very common operation in mathematics. All right, now we'll first consider the very first case here. Case 1 is the plus condition, okay? So what I did is I added n squared to both sides, and we have m squared isolated. Now this next step is kind of counterintuitive. I had to look up the solution on this. I couldn't figure it out myself. If you'll take a look right here, m plus 1 squared is of course equal to n squared plus 2m plus 1. But notice that's greater than n squared plus the square root of 1 plus 36n whenever n is greater than 8. And let's just write down, this wasn't clear to me at all when I first looked at it, but it turns out that 2n plus 1 is strictly greater than the square root of the quantity 1 plus 36n. Excuse me, let me erase that. 1 plus 36n. Now, again, a lot of this is just kind of scratching around and checking the values of n, manually kind of. But so notice what happens, and you can just see here on the next line, when you substitute n equals 8 in here, when you substitute n equals 8 right here, you would actually get what, 19? Or excuse me, 17, right? 2 times 8 plus 1 is 17. Now right here, that would give you a greater than or equal to the square root of 289. And really, it's just equal. I'm being a little inaccurate the way I'm saying this, but notice that 36 times 8 is 288. When you add 1, you get 289. So this is actually equal. Okay, equal. Let me erase this. Oops. Okay, that's just equality right there, right, folks? So you can see if you have equality at n equals 8, okay, once you're greater than 8, this is going to be larger. Now, I didn't really show that, but it's very easy to see that if you square both of these, both sides of this, you would get that 2n plus 1 quantity squared is greater than 1 plus 36n, okay? So in other words, I'm merely asserting this, but you guys can verify that it does work out numerically. Now, the big step here that really helps us quite a bit is that we get m squared trapped between two other squares. All right. Now let me make this a little clearer here. Notice that this very first statement right here, this implies that m is strictly greater than n, right? M is strictly greater than n since m squared is equal to n squared plus some positive number, right? So that does imply that m is greater than n, okay? So that's why we get m squared is greater than n squared, right? M squared is greater than m squared is greater than n squared because m is greater than n, okay? Now, but look what happened right here, though. See, if 2n plus 1 is greater than 1, the square root of 1 plus 36n, you see you get this inequality in reverse. You get n squared plus the square root of 1 plus 36n is less than n plus 1 squared, you see? See right here, this and this? Okay, how that works out? That works out very nicely, okay, provided n is greater than 8. Okay, so it's kind of the reverse of what I was saying a while ago, okay? And so and remember, this part is just equal to m squared, right? See, m squared is just equal to this object, but we have this same object being less than m plus 1 squared, right? But you see, y'all, here's the rub. This is impossible, right? This is not possible. You can't have another square between two consecutive squares, right? So this is not possible, otherwise known as impossible. Not possible. All right, and so for that reason, all we have to do is check numbers less than or equal to 8, okay? If we can't have this condition occurring for n greater than 8, that just means we have to check the numbers 1, 2, 3, 4, 5, 6, 7, 8, okay? Now, it turns out, I just cut to the chase, y'all. It turns out that 8 works, and you can see this. Let me just go ahead and write this down. Right here, this would end up being m squared, okay? Now, 8 squared is, of course, 64. Okay. Now, so this piece right here is equal to 1 plus 36 times 8, y'all. But again, that's 289. It's equal to 289. 36 times 8 is 240 plus 48. That's 288. And 288 plus 1 is 289, right? But what does that tell us? That tells us that m must be equal to, again, by inspection, plus or minus 9, right? And folks, isn't that kind of cool? 9 squared is 81. 81 minus 64 is 17, right? And of course, squaring the negative 9 gives you the same result. So what does that tell us, folks? What does that tell us? That tells us we have 2 more solutions, namely plus or minus 9 as your m coordinate and 8 as your n coordinate. All right, so you see now we have 4 solutions. This plus or minus 9 and 8, and then up here we have the trivial solutions that we just about 5 minutes ago, right? Just by looking at it. All right, now we also have a case 2. Remember, we have a case 2 that involves the minus. Here we did the plus. All right, we did the plus, but so we have to consider the minus also. Now, y'all, the logic, I decided not to work that case out. The logic is very, very similar. You go through a very similar process of putting numbers between two a square between two consecutive squares. And what you get right here, and again, if you guys want to work this out, it's kind of neat to see it happen. But you actually get plus or minus 10, I believe. Plus or minus 10, comma 8. Okay. And again, the setup is, I mean, it's very, very, very similar. Okay, so I'll just put that down. It's similar to case 1. Similar to case 1, just the inequalities are sort of in reverse. So y'all, that does it. We have 2 solutions here. Plus or minus 10, comma 8. We have 2 solutions here. Plus or minus 9, comma 8. And then also we have 2 solutions at the very beginning. So we have a total of 6 solutions. to this integer equation. And again, the key observation was this step right here, getting to a point, finding a break point, if you will, for where the inequalities would hold, and getting a circumstance where you had an impossible condition. And what that does, that limits. All you have to do, I just showed it to you for 8, but I also checked for 7. 7 doesn't work, 6 doesn't work, 5, all the way to 2. Okay. Again, so this was an important terminate condition. It kind of cut down on the number of values we had to do computations on. We can rest assured that no number greater than 8 would be a solution because of this impossibility right here. But anyway, I hope you enjoy. Thanks for viewing.